Every takeoff represents a critical operational compromise between community noise mitigation, maximum aerodynamic efficiency, and fundamental flight safety. Under ICAO DOC 8168 and EASA standards, modern Airbus operations require far more than rote compliance. They demand mastery over automation transitions, energy awareness, and immediate tactical adaptation when conditions diverge from the nominal flight profile. From a physics perspective, flight path trajectories do not eliminate acoustic energy. They determine where that energy is distributed. High-thrust jet exhaust shear creates severe peak noise directly below the climb path, mitigated only by rapid vertical climb. Conversely, prolonging time in a high-drag configuration extends the overall sound exposure level downrange. Selecting a noise profile is fundamentally a tactical reallocation of acoustic footprint. These competing acoustic goals divide standard departures into two spatial strategies. NADP1 is our height focus, holding takeoff configuration and V2 plus 10 to 20 knots up to 3,000 feet to shield close-in communities. NADP2 is our speed focus, initiating forward acceleration and scheduled flap cleanup at or above the 800-foot regulatory floor to minimize distant exposure and clean the airframe early. From an airline efficiency and engine longevity standpoint, NADP2 is the clear global benchmark. Holding an aircraft in a high-drag configuration to 3,000 feet under NADP1 imposes a severe fuel penalty of up to 200 kilograms per departure and elevates cylinder head temperatures. The brief 1 decibel rise in close-in noise under NADP2 is heavily outweighed by substantial overall reductions in fleet fuel burn and total trip emissions. Inside the flight management system, flight envelope safety is hard-coded into the logic architecture. The system enforces a strict rule. Acceleration altitude must equal or exceed thrust reduction altitude. If an acceleration altitude lower than thrust reduction is entered, the FMGS automatically rejects or corrects it, preventing premature pitch down and uncommanded speed acquisition before climb thrust is locked. During departure acceleration, flap and slat retraction is strictly governed by fact-computed characteristic speeds to preserve the 1G stall buffet margin. Retracting flaps below F-speed or slats below S-speed compromises high-angle AVATAC protections. Because these dynamic targets are derived directly from the initialized zero fuel weight, accurate gross weight data entry on the ground is the single foundation of aerodynamic safety aloft. Executing NADP1 requires disciplined monitoring of the flight mode annunciator. Pitch targets V2 plus 10 to 20 knots in SRS mode through initial climb. At 1,500 feet, the lever climb flashes, prompting the reduction of thrust levers to the climb detent, updating the FMA to thrust climb while remaining in SRS. Only upon reaching 3,000 feet does SRS disengage to climb, lowering pitch to accelerate and clean up on a schedule. In NADP2, thrust reduction and acceleration are harmonized into a single operational event. Passing the program dual altitude, typically 1,000 feet, the levers are retarded to climb. The FMA transitions instantly to thrust climb. SRS disengages simultaneously, prompting the flight directors to lower pitch rapidly toward green dot. The pilot monitoring must anticipate this rapid acceleration and command flap retraction without hesitation. At high takeoff weights, a dangerous trap emerges during NADP2 acceleration. Moving the flap lever updates the PFD-VFE display instantly, but the physical wing surfaces lag behind. With climb thrust active, the aircraft accelerates aggressively. And if the pilot delays calling flaps 0 above S-speed, airspeed easily overruns the physical structural limit of the retracting slats, triggering an avoidable overspeed warning.VFE. In the event of an engine failure after V1, all environmental noise abatement procedures are instantly terminated. SRS pitch guidance immediately shifts from speed preservation to maintaining takeoff safety speed V2. Auto thrust is bypassed, maximum available thrust is commanded, and the high lift configuration remains locked until reaching the published engine-out acceleration altitude. Obstacle clearance is absolute. Aviation regulations worldwide dictate that flight path integrity overrides local noise abatement rules whenever adverse weather threatens departure safety. If crosswinds exceed 15 knots, tailwinds exceed 5 knots, the runway is contaminated or convective wind shear is suspected, crews are legally obligated to suspend NADP, maximize vertical climb gradient, and preserve total energy margins. Technological advances on the A320neo cut departure noise by roughly 50% at the source through ultra-high bypass architecture. However, the 1.8 tons increase in engine dry weight required Airbus to recalibrate fly-by-wire rotation laws and expand physical rudder deflection by 5 degrees. The Neo's exceptional climb performance accelerates through speed gates even faster, demanding earlier crew anticipation during cleanup. Consider a sudden engine flameout at 600 feet AGL. As the aircraft passes the nominal 1,500 feet thrust reduction altitude, the lever climb will flash out of standard automated sequencing. The fatal error here is instinctive muscle memory. Pilots must never retard the operating thrust lever. Ignore the prompt, maintain toga, hold the takeoff configuration, and climb uninterrupted to the published engine-out acceleration altitude. Line operational excellence requires deep systemic knowledge, not rote script repetition. Understanding why the FMGS enforces acceleration boundaries, how structural aerodynamic limits trail PFD visual cues, and how to stabilize raw data departures ensures that flight crews command the automation with authority, eliminating startle effect in demanding line environments. To summarize our non-negotiables, terrain clearance always supersedes noise rules. Never initiate cleanup below 800 feet. Verify every mode transition on the FMA rather than assuming lever position. Retract flaps precisely at target speeds to protect trailing edge surfaces, and immediately abort noise procedures under weather or engine emergencies. Fly the aircraft first, manage the energy, and stay ahead of the profile.